I'm going to present the Landslide Hazard Map of Bogota. Let's begin. The agenda for today is the context of landslides in Bogota, which is methodology. This is an approach that we use to get this map. The other one is MPN methodology. I will explain this later in detail. Then we have contrasting maps. Afterwards, we will have software and view processing, impact and results, and conclusions. So, the context of landslides in Bogota. This map, this work, is part of a land management plan, which is an instrument to plan the territory, considering economical, social, and of course the land use of the territory. Let's see where is the place where I'm talking about. So we have here this is South America, and then we have these countries: Colombia, Ecuador, and Peru. And we share the same conditions because of these Andes. So we have similar conditions, and we have a lot of landslides. And now we have here Colombia, and here is Bogota. So Bogota is in the middle of the country. So here we can see how is Bogota conformed. So we see the slope, and then the rivers, wetlands. And we analyze for this study only this and this area. So we analyze only 16,000 hectares. So we have the Bogota, the height is 2,600 meters, but the maximum height is 4,000 meters. Also, Bogota is located in the tropical convergence zone, and the population is about 8 million. So we can here see that Bogota is divided into zones. One is flat, as you can see, and the other one is just mountains. But why a landslide occurred? What is the reason for this? Well, the main reason is the gravitational force. Then you have the gravitational force, but we have also two components: the shear force and the normal force. Normal force is of course perpendicular to this plan, but you also have the shear strength. And then, if the stiffness is increased, like in this case, then the shear force and the shear strength are almost equal. So this landslide could happen or not. That depends on rain, angle, and material. So if there is a big rain, there is a frequent rain, like is common in Bogota, then this block will be saturated, and this block will fall down, of course. And in this case, it's obvious that the stiffness is very high, and that's why there is no doubt that this block will just fall. And then we have all the ingredients to landslides that they could happen. So we have frequent rains, we have mountains, we have an intermediate zone of earthquake, and the mountains have a natural susceptibility due to geomorphology and also the geology that influence slides. So the materials are also not good. But also the frequent precipitation and the global climate change play an important role. And phenomena like El Niño, La Niña, had an influence. But this is not the whole picture. There is also a social problematic, and that means that there is an accelerated growth of the people of urban, a disordered urban growth. And the people live in high-side regions. They don't have anything to do. Just go there. You can see here the mountain, and they live just here. So there is a human activity in quarries, in the slope of rivers and streams, and the steep slope zones and dams. Here, this is considered the largest landslide phenomenon in urban areas of Latin America, and its extension is 73.1 hectares. As you can see here, the house is cut up, and there are cracks of 1 meter wide. So this one is very, very dangerous. I would like to show you now the variables that we use to get this methodology, and I would like that you focus only in this part. I will show you the variables very, very fast because we don't have time. But just try to see what is in this part. So the first approach is, of course, has to do with a stability evaluation system. So here, this methodology consists of categorizing and weighting of factors that influence a landslide. And there is material, terrain conditions, drainage, land use, erosion, climate, earthquake, and human factor. And here, then we see that the best rating will be in green, and the worst will be red, and the intermediate will be yellow. Now, here we have the susceptibility factors. As a susceptibility factors, we have drainage, terrain conditions, material, and land use. And for example, to explain how these variables were evaluated, we have here that the drainage density was measured in meters divided by hectares. Then we have the classification as high, medium, or low. Then we have these numbers, but this is important thing here. Average loss of drains, if it is low, medium, or high. So if the slope is low and the drainage density is low, the rating will be the biggest one. That will have biggest one, like here. So that means that 35 is the best rating for this variable. So these areas in green are good for this variable, for drainage. Now I will show you the other variables. So we have terrain conditions. Here I would like to say that I use SAGALIS to do this. SAGALIS is an open source program that has a lot of terrain analysis routines. So it is a program which is worth to be explored. Then we have a material. Are you looking always in this area? Is looking. Just focus in this. What is the color of the Bible? Here we see that there is a green, but has a little bit of red. We will see what is with the other. The material, then we have to analyze the geology, geomorphology, and the structural geomorphology and geology. Then we have the land use. There is a combination of the slope map and coverage type. And now we have the triggering factors. Of course, the triggering factors are very important, and the human factor plays a very important role. For the human factor, they will consider minor activity, drinking water system, sanitary sewer system, road status, and required buffer zones. And then we have erosion. For erosion, it's important the verisol and processes map. Climate, this has to do with return period and rainfall. Earthquake. That's all. So at the end, all these variables were combined, and the result is this one here. So can you see this part is red? At the beginning, I said that this is the largest phenomenon of landslide in Latin America, with 73 hectares. So it is already red, and red is bad. Okay, and now I will like to talk about the second approach that was used. This is a probabilistic approach, and I will not go into detail to these things. I just want to say that the height is related to the length. I will explain what the height and length are. So for doing this, it was necessary to make a slope families delimitation, families of slopes. So as you can see here, all these lines, you see all these lines. There are families of slopes, but these colorful areas were obtained by means of hydrological modeling, because we needed homogeneous areas, so they are watersheds, but they have been intersected with the flow accumulation. Then in this way, I have, of course, if you have the flow accumulation, so where the water runs, and then you have here an homogeneous area and here an homogeneous area. So we have then, we have to have then the coordinates. Oh, sorry. Here was needed to calculate the intersection of these contour lines with these lines, which are slope families. Now that was performed with point coordinates. It's not a difficult task. You have the intersections, but then you have to separate the families, because here you see that each family has a name. So I needed that each family was separated in a file. So for doing this, I use this model, and I use this iterator, and then I have to find the height and the length. So what is the height? Here I needed to find the distance between this inferior contour line and this. So the distance between this yellow point and this, and so on. This yellow point and this yellow point and this. And then the next measure was here this yellow point and this yellow point and this, and so on. And for each row, I had to calculate the average, the maximum, and the minimum. So for doing this, for example, in only this region, you have 79 intersections. So for doing that, that's why I use an application. I created a small application. This is just, it was an Excel. So here I have the coordinates, the elevation, and the slope name. And here I just say execute. Sorry. Oh. What should we do? Here. So I have the coordinates here in this part, and then I have to find the distances. because it was already drawn. Okay, let's make this automatically. It's already done. Then here I have the distances. It's clear. It's about the distances. It was clear. Okay. I just want to make emphasize that it was not that easy, that if you do this manually, it would not be an easy task. That's why you have to do it like automatically. Then this result was just copy here. Yep. And this I gave you to the specialist in geotechnics. So I will not talk about the geotechnical modeling. This is very complex. But at the end, I have points which are located in the whole studied area. So here and here. And then afterwards, I made an interpolation with the safety factors. And afterwards, these two partial results that I have from the first methodology, from CES methodology, and these ones, which are obtained with the MPN methodology. So this is a statistical methodology, and this is probabilistic methodology. They were combined using this matrix. So if I had a medium here in MPN methodology and medium in CES methodology, I have M2. This is a conservative way to evaluate the result. And then afterwards, the processes were added, and then they were used to calibrate these results. So these processes were a landslide inventory that collects information. So these events already happened. So the active process was very high, incipient process was high, collapse process medium, and stabilized process was low. And the instruments are technical studies, so technical concepts, and they were in a scale like this, very detailed scale, so they were generalized, and then they were included in the final product. So just to summarize, I have NPN methodology plus CES methodology. And afterwards, I have the processes, so the inventory of these landslides. And they were, for combining this matrix was used. So here we can see that the processes had a high preponderance, because here very high and very high is very high. But always when the processes were very high and high, it was most important than this result. And then we have the instruments. And this is the final one. For software and reprocessing, I would like to say that for automation, I use the RP library from Python. And for combination of these variables, it was used GRASS. But GRASS was used also in this case, in the smoothing part. So you can see here, this is the original dataset. And then here, I use a commercial software for smoothing. And then you can see that there are holes. So afterwards, then I decided to use the algorithm checking from GRASS, and the result was much better. Important to mention is that the correction of the topology. So as we work with vector, we have problems about the topology, and GRASS was used successfully for correcting these holes again. The impact and the results. As we can see, 64% of the area of the studied area is in medium hazard. So here, and here the problematic area is in red. So from this map, New suitable areas for housing maps can be defined, and also it is important the continuous monitoring of likely zones to suffer a landslide, of course, and special attention should be paid to medium and high hazards. This map is important for prevention, but it should not be the only element that is used. Now, this is the place that I showed you at the beginning, and they made mitigation construction work here. This is a wall whose length is 200 meters and 10 meters high. But 3,000 families were relocated. Conclusions: in processing of large volumes of geographical information, other alternatives different to software and commercial software should be used or tried, at least, like GIS or Saga or open source software. And also, it is important to have into account that the simplification of the model is a simplification of the reality. So this is possible that some variables were not taken into account. That's all.
Johana, thank you a lot for your presentation. We start with the question: how could continuous monitoring look like?
Well, they have groups of people who are continuously evaluating the areas, and they go to the places which are more susceptible to software landslides.
And how does that evaluation, like inspection or what?
Yes, this by inspection they made some measurements. Yes, yes, and then it is included for updating the maps.
And was construction of this wall initiated by your results, or was it independent?
This is independent. This was discussed before because this is a very new map. This was performed in 2016. This is really new.
Questions? Yes, Manuel, please.
So thank you for that wonderful presentation. How did you take or record those points data that you shown in your presentation? A lot of point data. How did you record them? Did you use
Which data?
you shown? Are you? You chose on my point data displayed on the map there.
Point data. Yeah, point data on the map.
Point
Point
data?
data, yeah.
You mean these intersections between the contour lines and the slope?
Just on my. Can you just show your technique? Where is the coordinates?
The coordinates, yes. I measured it. So we have the contour lines, and then the technical specialists made these slopes. And then these intersections were just made by intersection in ArcGIS. And then I had a lot of coordinates. And then I used this application in Excel for just organizing a little bit.
Early warning systems are installed in these areas.
Sorry?
Early warning systems installed in these areas. You identify some
approaches for early morning in this area.
automated systems.
That is a big issue. That is
Because actually my country also have very high risk of landslide. We installed, we found a few places like this. Then we installed automated warning systems.
yes.
Yeah, it's working perfectly now.
It is not
This
very
can be the input. This can be the one of the inputs of the.
Actually, the rainfall, so we can find out the landsliding prone areas from these kind of studies. Then In the early warning system includes the rainfall, then actually we can set the rainfall. One factor is rainfall, right?
Yeah.
So there are so many factors.
Yes.
So if the rainfall is this area is more than 50 millimeters per hour, then definitely we can give the first warning. They have to go out from the houses and residence areas.
Yes, there is something like an evacuation program. And they are monitoring constantly this, for example, this rainfall. So if there is a frequent precipitation, a very strong precipitation, they will evacuate the people.
Okay. So,
in the CES model, one of your criteria was the human factors.
Yes.
And you have this list of, yes, for example, drinking water and all this. Will you explain briefly how you classify this information? Yes.
So the mining activity. So if the mine was active, they give a rating. If it was abandoned, a different rating, and so on. For example, for this sanitary sewer system, the people or the houses which don't have sanitary sewer system are more susceptible because they just throw the wasting water just down here. Yeah, and then this is more susceptible. No. And also the road status. If a road is not enough, if this road has not enough payment, yes, the 80% is not payment, then